Assalamualaikum and hi everyone. This is pre-recorded video 17 for chemical bonding. In the previous video, we have been introduced to hybrid orbital theory, part 2, where we learned the formation of sp, sp2, sp3, and other types of hybridizations. So now we are going to learn more about hybrid orbital theory, and this is part 3. We can begin with the questions how to predict hybridization schemes. In hybridization schemes, one hybrid orbital is produced for every simple atomic orbital involved. And the procedure or the steps to make the prediction is first, write a plausible Lewis structure for the molecule or ion. Second, we can use the VS-EPR theory method, okay, to predict the electron group or electron domain geometry of the central atoms, for example tetrahedral or octahedral, okay. And then third, select the hybridization scheme that correspond to the VSEPR prediction, okay. And lastly, describe the orbital overlap and molecular geometry. So these are the 4 steps that we can use to predict hybridization schemes. Let's do some practice. Answers are already given, but you need to show how do you get the answer. Please refer to your lecturer for more clarification about this. So we take an example for molecule XeOF4. At ground state, this molecule has the electronic configurations, valence electronic configuration of 5s2, 5p6. For excited state, the 3 electrons from 5p excited to d orbital forming sp3 d2 orbitals, hybrid orbitals. Okay, the sigma bond are formed between xenon and fluorine, which is 4 of them, and 1 oxygen. Another one is pi bond by p orbital overlapping with oxygen, leaving 1 lone pair from 5s. Let's do more practice and please check the answers with your lecturer. Beryllium chloride follows hybridization for sp. Okay, so beryllium chloride is BeCl2. We know it will produce a linear molecule, and sp orbital is shown in the slide. Sp contains s and px orbital, combination of s and px orbital. Py and pz are left empty. Okay, so you can see from this caricature, okay, so it's actually sp, only sp hybrid orbitals involved, leaving py and pz empty. While for boron trifluoride, the hybridization involved is sp2. We have discussed this in the previous video, actually, the isolated V boron atom. Okay, so this is isolated boron atom, and then when it goes towards hybridization, you can see the 3 sp2 here, so it becomes 1 sp2, 2 sp2, and 3 sp2, and then it left 1 empty 2p. Okay, so and then it's end up the p orbital from f or fluorines overlap with this as these 3 sp2, 1 2 3, to form bf3. This is another example for sp3d hybridization. The ground state of phosphorus transformed to hybrid sp3d, then overlap with the p orbital from chlorine. Okay, so this is the original or ground state, and then this is a hybrid state sp3d, and then each sp3d orbital overlap with p orbital from chlorine to form PCl5. Same goes with sp3d2 hybridization in sulfur hexafluoride. The ground state of sulfur transformed to hybrid sp3d2 from 3s and 3p and 3d. Okay, so this is the ground state, and then this is a hybridized state. So this is actually 6 sp3d2. Why 6? Because s1 and then p 1 2 3 and then d 2 of them, so sp3d2. So 6 orbital altogether, and then the sulfur can this orbital of sp3d2 can overlap with p orbital from fluorine to form sf6. A problem to consider, okay? Describe the bonding in H2O according to valence bond theory. Assume that the molecular geometry is the same as given by the VSEPR model. From the Lewis structure of Lewis formula for a molecule, we can determine its geometry about the central atom using the VSEPR model. First, we draw a Lewis structure for water. From this geometry, we can determine the hybrid orbitals on this atom or central atom, which is oxygen, assigning its valence electron to this orbital one at a time. We note that there are 4 pairs of electrons about the oxygen atom. And according to VSEPR theory or model, these are directed tetrahedrally, and from the previous table you see that you should use sp3 hybrid orbitals because this is ax2 e2. Okay, the notation for VSEPR is ax2 e2. Then each OH bond is formed by the overlap of one s orbital of a hydrogen atom with one of the singly occupied sp3 hybrid orbitals of the oxygen atoms. That's the end for hybrid orbital theory part 3. Thank you. See you in the next video.